Hey, yo, welcome back for another deep dive. Today, I thought we'd tackle something that's been really messing with my head lately. It's one of those daily coding puzzles from AI Codecast, you know?
Ah, yeah, those can be real brain
It
twisters.
really can.
Yeah.
And this one, well, it's all about finding the fastest way through a grid. But there's a twist. Like each cell in the grid has this kind of timer on it. You have to wait a certain amount of time before you can even enter.
So you're saying it's not as straightforward as just finding the shortest path. You might have to factor in waiting time, which could make a longer path actually faster overall.
Yeah, exactly. It's like
Yeah.
it's counterintuitive, right? It reminds me of like those old adventure games where some doors only open at certain times.
Yeah, I see. So sometimes it's better to hang back and wait rather than rush ahead, potentially getting stuck.
Exactly.
Interesting.
And that's what makes this problem so tricky. So imagine a grid, like, a chessboard or something.
Okay, got it.
And you start at the top left corner, right. The goal is to get to the bottom right. You can move up, down, left, or right, one cell at a time. And each move takes, say, 1 second.
Okay, standard grid movement.
But here's the catch. Each cell also has a number on it.
And that number represents.
It's like the minimum number of seconds you got to wait before you step into that cell.
Mhm.
Like if a cell has a 5 on it, you have to chill somewhere else for 5 seconds before you can enter.
Got it. So the challenge is to figure out not just the path, but the timing of your movements to minimize the overall time, right?
Right.
Including all that waiting.
Yeah, exactly. And, when I first saw this problem, my first thought was, okay, let's just try every single possible path.
Ah, the classic brute force approach. Just try everything and see what sticks.
Exactly. But as you can imagine, that gets pretty messy pretty fast, especially if you have a large grid.
Yeah, I can see how that would become computationally very expensive very quickly.
Right. So we need to come up with something more efficient, some clever way to find the fastest route without checking every single possibility.
Some kind of shortcut, so to speak. What are some common pitfalls that people might fall into when trying to solve this? What should they be careful of?
Well, one thing I noticed is people might forget that waiting time actually counts towards the total time. It's easy to focus on the shortest distance, but even if you have to take a slightly longer path, it might be faster if it means you spend less time twiddling your thumbs.
Yeah, that makes sense. It's easy to overlook that waiting is an active part of the problem.
Another tricky thing is understanding exactly how that activation time works. It's not, the time you arrive at the cell. It's the earliest time you can actually enter the cell.
Oh, I see. So if a cell has an activation time of, say, 5, and you get there at time 3, you still have to wait another 2 seconds, right?
Yeah, precisely. You can't just magically teleport in and wait. You have to actually move to get there, and each move takes time.
I'm starting to see how this gets complicated. So if you arrive too early, you might have to, like, move to a neighboring cell and then back again just to kill time and make sure you hit that activation time just right.
Yeah, exactly. It's like trying to time your arrival at a train station. You don't want to get there too early and miss the train, but you also don't want to be late.
Right. So there's this delicate balance of timing and movement that needs to be carefully considered. It makes me think, how do we even begin to keep track of all these possible arrival times and waiting strategies? What tools can we use to manage all of this?
Hmm. Well, I guess the first thing that pops into my mind is maybe we could use a priority queue.
A priority queue, like those lines at the airport where people with like first class tickets get to board first.
Yeah, kind of. But in this case, the priority would be the estimated arrival time at each cell. So the cell with the earliest possible arrival time would be at the front of the queue.
Ooh, I see. So we're always picking the most promising cell, the one we can reach the fastest, to explore next. Exactly. That way we're not wasting time exploring cells that we know we can't reach for a while.
Okay, I'm starting to get the hang of this, but um, how do we actually factor in those pesky waiting times into the arrival time calculation? Seems like it could get kind of tricky.
You're telling me, remember, each move takes time, right? So even if we arrive at a cell early, we can't just sit there and wait. We might have to move to a neighbor and then back again to kill time.
Ah, like doing a little dance around the grid. But how do we actually account for that extra movement time in our calculations? It seems like it would add another layer of complexity.
Okay, so let's say we're at cell A and we're thinking about moving to cell B.
Okay, cell A to cell B.
Got it. And let's say cell B has an activation time of, let's say 5.
Activation time of 5.
Now, we need to figure out the earliest time we can actually enter cell B, considering both the travel time from A to B and any potential waiting.
Right, because just getting there isn't enough. We have to be able to enter.
Exactly. So let's say it takes, 2 seconds to travel from A to B, and our current time at cell A is 3 seconds.
Okay, so if it takes 2 seconds to travel from A to B, and we're at A at time 3, that means we arrive at B at time 5, which is exactly when it activates.
But here's the catch. We can't just sit on cell B for 2 seconds while we wait for the activation time, right? We have to move. So we might need to move back to cell A and then back to cell B, which would add another 2 seconds to our total time.
Ooh, sneaky. So the actual earliest we can enter cell B is time 7, not time 5. We have to, like, factor in those extra moves to kill time.
Precisely. It's like trying to find a parking spot. Sometimes you have to circle the block a few times before a spot opens up.
So our priority queue keeps track of all these potential arrival times, always choosing the cell with the earliest time to explore next. And for each cell, we got to carefully calculate the actual arrival time, taking into account those activation times, travel times, and all those little waiting maneuvers.
Yep, exactly. It's a bit like a carefully choreographed dance where every step has to be timed perfectly.
This is making my head spin a little.
Yeah.
But I think I'm starting to see the logic behind it. It's definitely a lot more efficient than trying every single path, that's for sure.
Oh, absolutely. And as we explore each cell and its neighbors, we update the priority queue with the most up-to-date arrival times. So it's like our queue is constantly evolving, guiding us towards the optimal path.
Okay, this is all making sense. But before we get too comfortable, I have a feeling that there might be some tricky edge cases we need to think about. Like, what if we get to the starting cell and we're immediately stuck? What if there's no path at all because of those activation times?
All right, so picture this. You're at the starting cell, the top left corner, all set to go right. But both the cell to your right and the cell below you, they both have activation times
Yep.
greater than 1.
Oh, okay, so I can't go right. Got to wait more than 1 second. Can't go down either. Same deal. I'm trapped before I even start.
Exactly. You're totally boxed in. There's like literally nowhere to go to wait for those activation times to tick down.
That's a sneaky one. So our algorithm, like right off the bat, needs to check if we can even make a move. If we're stuck like that, we can just say, nope, no solution here.
Exactly. It's a simple check, but it can save us a ton of unnecessary computation. We don't want to spin our wheels if there's like no way to get to the destination.
Right, right. Efficiency is key. Okay, so we've talked about the problem. We've brainstormed some potential pitfalls, even uncovered this sneaky edge case. I think we're ready to put it all together.
I think so. I think we've got all the pieces of the puzzle now.
So just to recap, we start by checking for that initial edge case. Are we stuck at the start? If we are, game over, no solution.
But if we can move, then we initialize our priority queue.
Right. Got to have our trusty priority queue.
And the first element in the queue is our starting cell, and its arrival time is, 0, because we start at time 0.
Okay, makes sense. And then we enter the main loop of our algorithm, the heart of the operation.
Yeah, and we keep looping until we either reach the destination or our priority queue is empty, which would mean there's no possible path.
Okay, so in each iteration of this loop, what exactly happens?
We grab the cell from our priority queue that has the lowest arrival time, that's our most promising lead, the cell we can reach the fastest, right? And then we explore its neighbors.
Got it. And for each neighbor, we calculate the arrival time, factoring in, well, all those details we talked about. The neighbor's activation time, the travel time from our current cell, and any potential waiting time.
Right. And that's where those tricky weighting calculations come into play. Remember, if we arrive at a neighbor too early, we might need to do some back and forth shuffling to a nearby cell to make sure we hit that activation time just right.
Yeah, it's like a little dance routine on the grid.
Okay.
Okay, so we've calculated the arrival time for each neighbor. What next?
Well, we check if this newly calculated arrival time is better than the current best known arrival time for that neighbor. If it is, we update the arrival time in our priority queue.
So our priority queue is constantly evolving, always keeping track of the fastest possible way to reach each cell. It's like a dynamic roadmap guiding us towards the optimal path.
Exactly. And we keep repeating this process, popping cells from the queue, calculating arrival times, updating the queue
Until we pop the destination cell, the bottom right corner. That's when we know we found the fastest route. And the arrival time for that final cell, well, that's the minimum time to traverse the entire grid.
Yeah, it's a really neat example of how a clever algorithm can efficiently solve what seems like a pretty complex problem.
Absolutely. It's been a journey breaking down this challenge from AI Codecast. We went from like initial head scratching to a real understanding of the problem and a clear, efficient solution.
And, the real takeaway here isn't just the specific algorithm. It's the way we approach problems in general. Break it down, use the right tools, and think creatively.
Could have said it better myself. And to everyone listening, hope this deep dive not only cleared up this specific puzzle, but also gave you a glimpse into the fascinating world of algorithms. There's a whole universe of challenges out there, and AI Codecast is a great place to start exploring. So keep those brains buzzing, keep coding, and until next time, happy problem solving.